Hi. So, after our basic introduction to we have done a basic review of general computer architecture trends, more specifically some background on RISC architectures. With that background, we are slowly going to delve deeper into how GPUs operate in terms of their architectural details. So, we have always stressed on the fact that while we discuss about the RISC pipeline, we have always said that how a RISC processor will execute a single instruction using the standard fetch, decode, execute cycle, and at the end of that we also discussed how parallelism is handled in general purpose processors, and that also leads to some specific kind of processing that we know as vector processors. And as we know that GPUs represent a more specialized kind of vector processor which have been found to be very useful for general purpose as well as graphics compute loads. So, the question is, how is this data level parallelism handled? So, when we talk about data parallel algorithms, essentially these are algorithms that handle multiple data points in each basic step. So, this is a new term we have been talking about, that's data parallel algorithms. When we say there is parallelism in execution of a program, as we know that there can be parallelism resident at different levels. There can be instruction level parallelism, there can be thread level parallelism, but when we talk about data parallel algorithms, the specific thing that we mean is the algorithm has a sequential thread of processing, but in each step of the processing the work will be done on multiple data points simultaneously. So, it is like doing an add of multiple data points followed by doing a multiply of multiple data points followed by doing some other operation on again multiple data points, like that. So, if this kind of instances of computation is found very frequently in some algorithm, we like to call it a data parallel intensive or in general data parallel algorithm. So, typically as we can see that there can be several examples of graphics workloads and several other kinds of processings, multimedia computation, or there are several such example workloads which fit nicely into this notion of data parallel algorithms, and coming to the way they can be handled in hardware. So, of course, to handle such algorithms we require hardware processors that have the capability to exploit this parallelism, right? Now, as we understand that parallelism at the instruction level can be extracted in two ways, like we discussed earlier. It can be done at the compiler level, it can also be done at the hardware level. So, in a good case it should be a combination of two, that the compiler is able to extract some parallelism from a piece of code that has been written sequentially, and also the hardware while executing instructions is able to mark out which are the instructions that it can execute in parallel. These are the two fundamental types we have already explored. Coming to handling of data parallel algorithms, there are three popular techniques. The third one of course is the one that's general, this graphics processing units. The first one was vector processors. So, this was the early style of data parallel compute. Like if you are trying to do operations on a parallel set of data points, the same operation, then the solution that was proposed was vector processors. We will learn a bit about them. Then came the notion of specific instructions which will be part of normal RISC processors like x86. For example, some MMX instructions, that's the multimedia extension, or AVX instructions which came later on, the advanced vector instructions. So, these were kind of SIMD instructions or single instruction multiple data type instructions that became a part of Intel's x86 architecture, and they are essentially instructions which perform the same operation on a vector data type, essentially a set of data type which are homogeneous. So, that's something that came next. The earlier style of doing data parallel compute was vector processors, and as we know in recent times the idea of graphics processing units has caught everybody's imagination, and they represent the most modern technique of doing a lot of parallel computations in hardware together. So, coming to vector processor. So, what essential is the design philosophy behind a vector processor? It's fundamentally like this, that you have a register file in your processor. Apart from having normal, by normal I mean scalar registers, you also start defining what we call a vector register. So, what's a vector register? So, each vector register is a fixed length bank holding a single vector. So, say you have a length vector which is holding the different length values for the different dimensions of a house. So, that can be stored as a single type, it is a vector type of length. We will now start saying that it is not located in different registers, the different components of this type are not located in different registers, but they are all stored in a single register which is having a much bigger size, but it also has these compartmentalized parts, each of which has is kind of holding some specific component of the vector. So, each vector register is a fixed length bank, it holds a single vector. So, when I say that there is an operation, I am doing an operation like vector addition. So, there are two vectors v1 plus v2. I am having the content of vector 1 in one register, I am having the content of vector 2 in the second register, and they would get arrayed. Just as an example, so if I just say that I have two data points v1 plus v2. So, v1 is a vector, that means it contains components so both are n dimensional vectors and I am doing their addition. So, in a normal program, or let us call it a scalar program, so what I would ideally do is I will have a loop structure, and inside this loop structure, I mean there will be a condition here, right, and inside this loop structure I will have some add instruction which is doing addition of each of the components, right, and I break away from this loop structure when the iterator variable of the loop reaches n, right. Now, when I say I have this kind of vector instructions, I would like to think that instead of this I have some code which is like this. So, I have a specific instruction, let us say add.v, which represents its adding content of registers v1, v2 and storing it at some v. So, in a way what is happening is there is some functional unit and it is getting data from two vector registers v1 and v2, and the output gets stored in another vector register v. Now, the question is, this functional unit also needs to be a vectorized unit, that means it should also be able to work on this input data types in parallel, or maybe I may have lesser number of units which work multiple times fast enough to operate them. But the important thing is, we will come to this pipelining idea, but the important thing is instead of having a single scalar instruction, I have a vector instruction. So, basically a hardware instruction which when executed, so this is a vector instruction which when executed it operates on vectorized registers, and the vectorized registers have got fixed dimensions holding each of the components of the vector, and in that way the same operation gets done, maybe at a higher speed up. Why, we will come to that. Yeah. So, the vector processor will have a normal register file as well as this kind of a vector register file, and functional units may also be vectorized, essentially just like I explained that I can have an array of ALUs which can do addition, subtraction or other arithmetic operations in parallel. Of course, the original scalar registers are also present. Now, what was the first proposition in this space? Well, one of the most popular initial academic propositions was the idea of vectorized MIPS or VMIPS. So, VMIPS comprise the normal register file along with 8 vector registers. Each vector register holds 64 elements. Each of these elements were again 64 bits wide. That means these VMIPS would have been able to operate on vectors of dimension 64, and in each of the dimensions the number of bits that were there for holding some value in that dimension would be 64. So, let us just consider a small example here of vector assembly program. So, on the left hand side we have a normal MIPS code, and on the right hand side we have a vectorized MIPS code example. This is a standard example which you can easily find in the book on computer organization architecture quantitative approach by Hennessy and Patterson. For the time being, we assume that the vector sizes are less than the vector storage. That means we are working on data where the data type is vector, and that means it's like an arrays or I mean basically arrays, but the dimension on which I am working on those arrays, they are smaller than the vector storage possible in the architecture. That means let us say the vector registers have got 64 bits, that means 64 dimensions are allowed, and each dimension has got some fixed number of bits to store the value. So, essentially I am talking about working on arrays where the dimension of the array is limited to 64. So, here we are trying to do a simple scalar operation. So, you want to multiply a vector capital X with a scalar A and then do an addition with another vector y, right. So, with respect to that, if you look at the MIPS code, the non-vectorized scalar MIPS code, there are a few important things to notice here. So, in the non-vectorized code, you see there is this addition operation which is essentially implementing this addition of AXI along with YI. So, this addition operation is going to take one of the operands from the register F4 and store back the result to F4. So, it has got an input dependency with the multiply operation. Why? Because the other operand of this addition operation is in F2, and F2 is going to be updated by multiply operation previous to doing the addition. So, this multiply operation essentially does this multiplication of A and the ith component of X and stores it back to F2, and in the addition operation this has to be added with the content of F4 which is Y, right. Now, as we know that this is going to be done in a pipeline fashion. So, for the multiply operation to end, it has to write back the value of F2 to the register file, and that would happen in the last cycle of its execution, and until and unless that happens, add cannot really do the operation, right. So, add.d needs to wait for multiply.d. There would be a pipeline stall as we have seen earlier, and also if you look at the instruction s.d. So, .d of course means in MIPS mnemonics it means, I mean we are working on double data types, just to remember, and so this again has to wait for the execution of add to complete. Now, why is that? because the stored instruction s dot d, the store instruction is going to store the content of register F4 to some memory location, right. But this content would get updated by add previous to that, and then again for add to finish, the write back to F4 has to happen. So s dot d has to wait up to the point when the write back to F4 is completed for the add dot d operation. So as we can see, in the normal scalar implementation, I need to have the loop with the loop iterator variable I mean in each iteration I am doing practically axi plus yi, and then I am incrementing I. In each iteration I have the add, which needs to wait for the multiply, and also the store, which needs to wait for add. Now let us look at, and this wait has to be done in each iteration of the loop. That is the whole point here. If you look into the vectorized code, as we can see, this add instruction has to wait, this vector add instruction has to wait for the vector multiply instruction to complete, but wait how many times? Once. The vector store instruction needs to wait before the vector add instruction gets completed. Again, wait how many times? Once, because there is no loop here, assuming of course the dimension of the data size is less than the vector storage. But then again there is no loop here. Even if this assumption was not going to work, that means the data size was not less than vector storage, still then I would have a loop with much less number of iterations. The number of iterations would have decreased by a factor of this vector dimension. So you can understand how many cycles of waiting you are going to save if you have a vectorized code and vectorized hardware for executing the code. So overall the summary would be this: the vector processors, they will be executing scalar as well as vector instructions, and vector instructions pass a lot of parallel work to the hardware. Of course, there has to be that much parallel hardware based compute capability along with register banks which are vectorized. Now what about the functional units? The hardware must have parallel functional units, but it need not be like this, that okay, my vector registers are of size 64, so I need to have 64 ALUs. It need not be that. The functional units can be either fully parallel or a combination of parallel and pipeline units. It depends on how the hardware is implemented. For example, if the clock rate of a vector processor is half, doubling the number of lanes will retain the same potential performance. This is the standard optimization between pipelining and parallel processing. We will have an example for this. Now the question is, if I have support in hardware for such vector instructions, assuming that I have such support, is there some overhead for the compiler? Oh yes, there is, because then your compiler has to identify which are the segments of code that can be vectorized, where to emit a vectorized multiplication instruction and where it cannot emit a vectorized instruction. So this loop vectorization and handling of dependencies is something that has to be done by compilers working towards vector processors. Coming to vectorized hardware. So how can you really implement vector processors? Of course, as we understand that the good thing is I have less number of instructions to execute. Now the instructions may take less amount of time if I have lot of parallel hardware. It may take not so much little amount of time if I cannot really execute all the vectorized instructions, I mean all the operations in parallel. There has to be some trade-off, but this idea always holds that since I have much lesser number of instructions to execute, the number of waits in the pipeline would be less. So coming back to how vector instructions can ideally be executed. So let us consider a trade-off scenario here, that suppose I am just trying to show that there is a single lane of execution here. So I am assuming that I have this ALU nicely set up with its input being connected to two vector registers containing they are of dimension 10 each of them, and there is a single piece of ALU here. So I have been provided with an add.v kind of instruction, but then since there is only one functional unit, the adds happen seriously in a serial manner. But the good thing is there is not much of software assembly to execute. Only with that vectorized instruction, the entire pipeline understands that it has to operate a1 plus b1, and then it has to update the value somewhere, and then it will operate on a2 plus b2, update the value somewhere. It will do all the things, but in a serialized way due to the absence of multiple vector processing lanes. This is a single lane execution. What is the other option? Now suppose I have vector processing width just like earlier. I have vectorized registers of size like this, a1 to a9, let's say 9 size registers, but I don't have that much width in terms of vectorized lengths. I don't have that many parallel functional units. Let's say I have this kind of 4 functional units. Then what should ideally happen is the inputs will get distributed like this. So maybe they will be distributed in this kind of an interleaving. So the content of the B's, let's say they can be distributed by a4 followed by a5, a6, a7, again a8, again a9, like that. So across the different functional units. So I can say that, okay, although I have vector width of 9, but the functional units are present here are only 4. So I have some speed up, but of course the entire addition will not be a single cycle operation. It will take multiple cycles. Of course, in this case it will take less number of cycles with respect to this, but it will not get done by a single cycle. Again, just to repeat, the good thing here is I have a smaller assembly to execute. The pipeline is being told that you have to execute a vectorized instruction. So the number of waits are less, but how fast the instructions will execute depends on how many parallel hardware units are really present. With this background on vector architectures, let's just have a look on GPUs and their basic architecture. So this idea of parallel instruction handling by vector architectures, as well as the earlier well-known ideas like instruction level parallelism techniques, they were borrowed in the domain of graphics processing units, first to accelerate specific graphics workload, and then as we know that it has been found that they can accelerate most general purpose data parallel workloads also. So this is a snapshot of a sample GPU system, one of the earlier ones. This is a snapshot of the GeForce 8800 system, processor's basic block diagram architecture. This has been reproduced by me from the Hennessy Patterson's famous book again, which has also got a special chapter on GPUs. So as you can see that the host CPU and the system's memory connect through a bridge, and this is where the GPU will also be connected to. There is an interface with the bridge, and then there are certain functional units which will be slowly processing. What is important to note here is typically in the GPU you will have a hierarchy of processing elements. At the high level we have what we call as simultaneous multiprocessing units, the SMs, right? And inside these SMs you have specific processors which are known as the scalar processors. The popular names for these are SM stands for streaming multiprocessors, and SP stands for, there are two well-known terms that are generally used, streaming processors. So they are not streaming multiprocessors. Streaming multiprocessor is SM, the higher level in the hierarchy, and at the lower level each SM contains multiple instances of scalar processors, or in some books you will find the name streaming processors. So multiple instances of these streaming processors. And of course there are other units like for the memory, the cache, the shared memory, which will be covering one by one. So coming to this idea of GPUs. So if we take an example GPU architecture, as we know that there has been an evolution of GPU architecture in the last decade, and there are several well-known families of GPU architecture. So we start with one of the earlier ones, which was also very popular, the Tesla architecture. So the earlier figure depicts a GPU the GeForce GPU, with an array of 128 streaming processors or scalar processors cores, as we discussed earlier, and they are organized as 16 multi-threaded streaming multiprocessors. So, if we go back to this figure, as we said that there is a hierarchy here. Inside this hierarchy, I have 16 number of what we call as streaming multiprocessors, SMs. Inside each of them, we have 8 scalar processors or streaming processors, the SPs. Overall, I have got 128 streaming or scalar processors. Two SMs together are arranged as an independent processing unit called texture or processor clusters, or in some books it is also known as thread processing clusters. So, these are clusters. I have these clusters, 8 of them. Each of them contain these 2 SPs, and inside I have got 16 of the SPs, 16 of the SMs. Each of the SMs contain 8 SPs. So, in total I have got 128 SPs. The arrangement is each SM contains 8 SPs, 2 SMs together constitute 1 TPC. So, what really was the function of earlier GPUs? So, earlier GPUs were developed with a specific idea in mind that they should be there to accelerate the logical graphics pipeline. So, what is the logical graphics pipeline? It represents the standard API which is used for generating graphics for a computer. For that, there are a sequence of functionalities that need to be executed, and this is what the picture says. So, we have the input assembler followed by the vertex shader block, followed by the geometry shader block, setup and rasterizer, and then the pixel shader and raster operations, or in some places it is also known as output merger. Now, these are the well defined significant components of the graphics pipeline, which together provide a standard pipeline through which computer graphics is usually rendered. So, the idea is the software programs which really do that, they have a well known name that is called shader programs. Graphics applications send the GPU a sequence of vertices which are grouped into specific geometric primitives, points, lines, triangles and polygons. So, if you have an application and the application will try to render the output graphics on the screen, and for that it has to do the painting, essentially it is to execute the computer graphics algorithm to create the bitmap image of that. For that, it will require to execute this kind of a specific graphics pipeline which has got these 6 logically divided parts. For that, there are certain parts which represent specific programmable parts. These are the ones that we have highlighted here in blue. These are the vertex shader, the geometry shader and the pixel shader. So, why is this sequence there? So, as we have discussed that the graphics application will send this sequence of vertices. Now, these vertices needs to be processed by the GPU. The vertices may be grouped into specific different geometric primitives. They can either be in the form of specific discrete points, they can be in the form of mathematical objects as lines or triangles or polygons. The input assembler is the block which is going to collect these vertices and the corresponding primitives. The vertex shader is a software program which will map the position of the vertices to the screen, because finally it is the screen where they need to be rendered, right. So, this would mean a specific change in the values, that there would be a scaling and all that, and it will also mean altering their position, color or their orientations. After this vertex shader program's execution comes the next colored block here, which is the geometry shader. Now, the geometry shader program will operate on the geometric primitive. That means, it is going to operate on the specific graphics objects like lines and triangles which are going to be defined again, of course, as we know, by multiple vertices together, and they will change them or generate the additional primitives for them. So, usually what is these shader programs? I mean, how are they written and all that, because as we can see that there are this sequence of 3 shaders: vertex, geometry, and the pixel shaders, right. So, essentially the shader programs are data flow style of computation. That means multiple parallel threads can work on different data points and do some computation in parallel. So, we'll let's do something like we stop here for this lecture, and from this shader program and this style of computation is from where we will pick up in the next part. Thank you.